Okay, so we're beginning Unit 2 with the end of Chapter 3, but this is the beginning of Unit 2. And as you can see, we are going to be talking about linear regression some more. And linear regression is a subject that we have already used and discussed to some extent in Unit 1. But the way that we used it in Unit 1 was basically just as a shortcut to finding the equation of a line, but it's not really the point of linear regression. So what we're going to talk about now is really the proper use of linear regression. Furthermore, this is going to involve a lot of calculator work, so I just want to point out that you do have full calculator instructions for linear regression on ELC in the content area under TI 83-84 methods. All right, so let's get into an example. This is the population of Portland, Oregon over a 50-year period in thousands. And what we're going to look at is whether or not this is a linearly distributed set of data and try to find a line that goes through it if it is linear and so forth. So the first thing that you would do is you've got to get this data entered into your calculator. So that would involve entering all these dates and then their associated populations in columns L1 and L2. And we can check the average rate of change using our delta list method for multiple average rates of change. And I'm just going to assume here that you know how to do this because we have done this already, so I'm not going to run through these steps. But you would input your delta lists in L3, and you see here that we have very different average rates of change over these intervals. So that definitely means that we do not have a linearly distributed data set. We can further verify this by looking at the stat plot of this data, and you'll see that it is definitely not a line. Okay. So there's that same set of data. So we know it's not linear, but what we can perhaps do, and this is really the heart of mathematical modeling, is we're going to approximate the data. And not just the data, but the trend of the data, like where the data is more or less qualitatively going. And the basic idea is that we want to say, well, what could we draw a line through this that would be a useful prediction or a useful predictor for further data points or for further times in the future or in the past, or even in between data points. Okay, so that's sort of what linear regression is really about. Notice here that I don't have two. What we've done in the past when we talked about linear regression is we just had 2 points and we found the line that exactly passed through them, and we used linear regression to find the equation of that line. What we're going to be doing here is not finding the line that passes exactly through all these points because there isn't one, but we're going to find a line that kind of comes close to all of them. All right, so we need to kind of drill into that idea a little bit. What does it mean to come close to all these points? And I'm going to skip to this slide right here, and I want to talk for a minute about model error, the idea of model error. So just looking at this picture, let me explain this. So these points right here are your actual data points. And this line is the approximating line. So it's the predicted. Okay. And since we can't find a single line that passes through all of these points, basically what we're trying to do is get this line as close to all of the points kind of overall in some way. And one way to do that is by looking at these things called model errors. And you can see at the top of the screen, the model error is the difference between the actual data value and the predicted data value. So say, for example, right here, our model error is basically that length right there. Now we also have a model error here between this point and this point, and here, and here, and here, and here, and here. This model error here that I've got this error drawn to, this would actually be a negative model error. And the reason why is because the actual value is smaller than the predicted value. And since our formula is, I've got it written up here as actual minus predicted, if actual is smaller than predicted, then this would be negative. And we would call this an over prediction because the actual value is smaller than the predicted value right here. Okay. So we have all these different model errors. This one under predicts, over predicts, under, over, under, and so forth. So we have a bunch of model errors. And what we want to do is sort of try to make all of those model errors small. Going back to this previous slide, to analyze a model error means the following. So if let's say we have n data points. So like in this picture, these are our n data points, 1, 2, 3, 4, 5, 6, 7. So we had 7 data points. We've got a model to approximately fit the data. And then for each of those data points, we define a model error, just like we were talking about. And it's the signed vertical distance from the data point to the model with the formula actual value minus predicted value, just like we were talking about. And then to kind of handle all of those errors in one computation, we have this thing called the sum of squared errors. And it's an overall measure of the model's error. So we're going to talk about the formula for the SSE in a moment. And then as long as we're talking about the SSE, there is a closely related other concept called the average error. And the average error is the square root of the SSE divided by the number of data points. So that it's averaged in the sense that it takes this total error and smooths it out over all the data points and then takes the square root. So what is this formula talking about? Because I still haven't really explained what this means yet. Well, we'll get to it soon enough, okay? But first of all, I guess the question is, how do we even get this model, this approximating model? Like, where does that come from? So one way to get a model, and this is the older way, is called the black thread method. And the black thread method was used before we had cheap computers and calculators. And so basically what you would do is you would graph the data and you just sort of eyeball a linear fit. Basically trying to get about half the data above and half the data below. Half data above and half data below. So, sometimes you can't do that. But, for example, I'll just draw a quick, easy one. If I have 1, 2, 3, 4, then we might have our approximating black thread. That's not a very tight thread, but anyway, might be something like that. I'm not sure if that's the best one, but it is an approximation. Okay. So for the Portland population data, I came up with this black thread method derived model. P of t equals 4.3t minus 8080. And now what I want to talk about is let's find the sum of squared errors and the average error of this black thread method linear function. Okay, and I'm going to go to my whiteboard and write some things down about the SSE. So first of all, sum of squared errors, that's the name of it. And that is really what we're looking at. So it's model error squared plus model error squared, and so on down the line. And we add all those up. We add all those up, there's all these squares of the errors, and that's the SSE. Okay, so it's sort of a computationally heavy thing to do, and so this is definitely something that you want to move to the calculator to do. And so I'm going to explain the SSE. Oops, let me start that again. I'm going to kind of write a rough procedure for the SSE with a black thread method line. Black thread line. Okay. So let's say that we have our black thread line and it's y1 equals some function f of x. Okay. Linear function. You go to your calculator, and the first thing that you're going to do is in column L1 you're going to put in your x values or your t values, your inputs. In